Now let's turn our attention to a gas dissolving in a liquid, typically water. So this is going to be the opposite trend than we see for solids. So from a solid to go to a liquid, it needs to absorb energy, right? It's typically an endothermic process. Now, for a gas to go to a liquid state, it's an exothermic process. We go from something with higher kinetic energy to lower kinetic energy, and so have to release some of that kinetic energy as heat. So because gases dissolving in water is an exothermic process, that means for all gases, the solubility is going to decrease as the temperature increases, right? So as temperature increases, solubility goes down. And hopefully this is intuitive if you've ever like opened up a warm can of soda or sparkly water or something like that. If the temperature of your carbonated beverage is really high, like on a warm day, when you open it, it goes flat very fast. The gas isn't as soluble in the liquid, the carbon dioxide. And so you'll lose a lot of it faster. It'll go flat and be just less of an enjoyable experience, or at least not the one you wanted when you cracked open a carbonated beverage. That'd be fizzy. And so we can see here's a table of the solubility of some common gases in water. I'm going to point out oxygen of these. So at 0 degrees Celsius, oxygen has a 0.0069 grams per 100 grams of water that's soluble. And as we increase that temperature, we by the time we get to boiling, of course it's 0, but even by the time we get to 50 degrees Celsius, halfway to boiling, like we've really decreased the amount of oxygen that'll dissolve. Um, Now, look at this is another interesting comparison to see. Look at the numeric value difference between things like nitrogen, oxygen, and carbon dioxide with sulfur dioxide and ammonium. They're like dramatically different. We're talking about something that's less than 1 gram for nitrogen, oxygen, and carbon dioxide dissolving in 100 grams versus like ammonium, it's 89.9. So in this case, more is going on than just a gas particle going from the gas phase to being surrounded and forming intermolecular forces with water and hanging out in the water. And what's happening is that the gas may be reacting with water. So when we see really high solubilities in water, typically it's because there's a chemical reaction that's taking place when the gas is surrounded by water molecules that then converts some of that molecule into something slightly different. And then that allows more of our gas to dissolve in our liquid. We also do see, though, that things like polar gases will have a greater solubility in water than our nonpolar gases, but most of our gases happen to be nonpolar. So if in fact, I'm having trouble thinking of one. So if you see higher numbers for solubility, it may be that you have a polar gas, or it may be that there's a chemical reaction taking place. So ammonium would be a polar gas, right? Got NH3. And so, but it was our gas that had the highest solubility. It's like 89 grams per 100 grams of water. It's crazy high. Um, and it's not just due to this polarity. It's because as that ammonium gas dissolves in water, becomes aqueous ammonium, it reacts with water in an acid-base reaction. It forms ammonium and hydroxide ions. And so we'll be able to keep kind of feeding ammonium into that chemical reaction until it hits equilibrium. And we're using these arrows right here. These mean equilibrium. And we'll talk about the equilibrium we see in chemical reactions in our next chapter, or a couple chapters from now. Now, another way you could increase the solubility of a gas rather than just decreasing the temperature is to actually increase the pressure, right? So, a gas that is under pressure, and we talked about this with kind of vaporization, right? We were talking about changing the volume or the pressure that there was for a gas over a liquid. And then when we increased that pressure, decreased that volume, we saw a increase in the rate of condensation. Took me a minute there. The rate of condensation. And then as that increased, we then hit a point where we were able to like increase our rate of evaporation and hit equilibrium again with this smaller volume, right? At a different pressure. Well, so our gas solubility then will increase as we increase pressure. As we apply more pressure or decrease the volume, we'll increase that rate of condensation or the gas being dissolved in the water or a different liquid when we're talking about forming a solution. And we can actually characterize this with Henry's law right here. And what Henry's law does is it relates the solubility of a gas to a constant times the partial pressure of the gas. So as the pressure of a gas increases, solubility will increase. So as that pressure goes up, we see the solubility that we would calculate go up as well. KH is that constant right here, and it's called Henry's law constant. And it's something that'll be unique for each different gas that you look at. And so here's a few of them right here. Henry's gas constant has units of molarity per atmosphere. So we're looking at the concentration per a unit of pressure. And so that's going to, when multiplied by a partial pressure for the gas, give us solubility in terms of molarity. So when we input that pressure, we're going to want to make sure that's in atmospheres. And so these ones are all at 25 degrees Celsius. You would need to look that up for a different temperature as well, which we're not going to worry about. We'll just stay at room temperature for this class. So here's an example that we can walk through about this. So we're at sea level. What is the solubility of oxygen in water? And oxygen makes up 21% of atmospheric gas. So if we're at a total pressure of 1 atmosphere, that's going to be equal to the pressure of our oxygen plus the pressure of our nitrogen plus the pressure of our argon plus the pressure of carbon dioxide plus the pressure of all the other gases that are in air. And we know that of all of the gases that are in air, 21% of the moles of any sample will be oxygen, right? And so that means really our partial pressure of oxygen here is going to be 0.21 times our total pressure, which is 1 atmosphere, right? So here. And the rest of the gases are going to then occupy the 0.79 times our total pressure at the sum of them, right? We're only focusing on oxygen, so we don't actually have to figure out the exact partial pressure of everything in air. So that means that our partial pressure of oxygen is going to be equal to 0.21 atmospheres if we're at 1 atmosphere pressure. So this is bringing back some of what we did with gas behaviors. So what would be the solubility of that oxygen in water? So the solubility of our O2 is going to be equal to Henry's constant times the partial pressure of our oxygen. So we're going to need Henry's constant. So coming up to our table right here, we can see that oxygen is 1.3 times 10 to the negative 3. So let's write that down here. And this is in molarity per atmospheres. So that's my KH. I'm now going to multiply this by my partial pressure, which is that 0.21 atmospheres, if we're at 1 atmosphere. And that'll give me my solubility of oxygen. And so that's going to equal, I'm going to get 2.73 times 10 to the negative 4th molarity.